Okay, so in the past videos we've looked at both delta H and delta S. Delta H and delta S both contribute to a reaction being thermodynamically favored. There are two different factors that need to be considered. And if we look at only one of the factors, we can make a prediction about whether or not a reaction will be thermodynamically favored. So if we look at delta H and we want to make a prediction, if delta H is negative, then we say it's favored, or we predict that the reaction would be favored. And if delta H is positive, we predict that the reaction is not favored. This is only a prediction, and in general this is true, but there are certainly many cases where a positive delta H is thermodynamically favored, because that's only one factor that we need to consider when we're looking at a thermodynamically favored reaction. The other factor we need to look at is delta S. Remember, S is change in entropy, or delta S is change in entropy. So if delta S is positive, in general, we can predict that the reaction is favored. And again, when we're looking at a reaction, we're looking at the system. So this is the delta H. When we're talking about either delta H or delta S, we're talking about the delta H or delta S for the system. So in general, positive delta S means the reaction is favored. Negative delta S means the reaction is not favored. Again, in general, that's true. However, there are cases where that is not true, because both terms need to be considered to determine whether a reaction is actually favored or not. So in order to look at the relationship between these two, we need to look a little more closely at the second law of thermodynamics. Okay, the second law of thermodynamics says a spontaneous process, one that is thermodynamically favored, they increase the entropy of the universe. So if we look at the entropy of the universe, which is system and surroundings, the entropy of the universe is constantly increasing. So that's all well and good, except it's really hard to measure the delta S of the universe. It's really easy to measure the delta S for the system, or relatively easy. It's relatively difficult to measure the delta S for the surroundings. So what we need to do is come up with a way to rework this in terms of just the system. So, as it turns out, and this is actually in the note packet on entropy and free energy, if you want to know how it can be shown, it's not that hard, I'm just not going to get into it right now. It can be shown that the delta S of the universe can be written in terms of the delta S of the system and the delta H of the system. So we get this expression right here. T delta S of the universe, and again, capital T is Kelvin temperature, because entropy, remember, units of entropy are joules per mole Kelvin. So Kelvin temperature, delta T. Negative T delta S of the universe equals delta H for the system minus T delta S for the system. So now this gives us a way to figure out what's going on in terms of just things that can be measured about the system. So the quantity T delta S is called the free energy change. And what this means is when we take into account the energy, because remember both delta H and delta S involve energy. So when we take into account all the energy changes that take place in a reaction, we can calculate what is left is called the free energy change. So that's the amount of energy when we take these two individual terms and combine them together. So for a process at constant temperature and pressure, think, for the most part, standard conditions, 25 degrees Celsius, 1 atmosphere of pressure. The delta G for the system equals the delta H for the system minus T delta S for the system. And typically you'll just see delta G equals delta H minus T delta S. This formula is on your formula sheet. It is a very crucial formula for thermodynamics. Okay, so as it turns out, If I do this calculation and delta G is negative, the process is thermodynamically favored. That is not a prediction. So negative delta G's mean the process is thermodynamically favored. If delta G is greater than 0, so it's a positive number, the process is not thermodynamically favored. And if delta G equals 0, then the system is at equilibrium, because at equilibrium, the forward and reverse reaction is taking place at the same rate, so there is no net change. So delta G equals 0, we're at equilibrium. We're going to talk about this next time in more detail. Right now, we're going to look at positive and negative delta G's. Okay. So some different calculations we can do to calculate delta G. Well, using this table of heat of formation and entropy values, we can calculate delta G. If we calculate delta H, if we calculate delta S, we can take those two terms and use them to calculate delta G. So delta H for this system is equal to the heat of reaction, heat of formation of the products, which is 2 times negative 396, minus the heat of formation of the reactants. And remember, elements in their natural state have a heat of formation value of 0. So the only number we need to take into account is negative 297. So if I do that math, I get a positive 198 kilojoules per mole reaction. So that's my delta H value. I can also calculate the delta S value by looking at the S of the products minus the S of the reactants. So the S of the products, SO3, is 257 minus the reactants. And now you notice heat of formation of oxygen is 0 because it's an element in its natural state. There is an entropy value for oxygen. So on this side, on the reactant side, I have 2 times 248 plus 205. That's my SO2 plus my O2. If I do that calculation, I get negative 187. And that would be joules per mole reaction, because again it's for a reaction, per Kelvin. Okay, now to calculate delta G, we use delta G equals delta H minus T delta S. Now the problem is that delta G is in kilojoules, or delta H is in the kilojoules and delta S is in joules. So you have to convert both of them to the same unit. And typically we convert everything to kilojoules. So delta H, or delta G, is equal to delta H, which is 198, minus T delta S. Since I have the little degree sign there, it's 25 degrees Celsius, which is 298 Kelvin, times the S value, which is negative 0.187 kilojoules, and that gives me a delta G of 142 kilojoules per mole reaction. And that's a positive value, which means this reaction is not thermodynamically favored. Okay. So, another way to calculate delta G is to use the same equation that we use to calculate delta H and delta S. We can use something called delta G of formation, the standard free energy of formation. Just like delta H, it's the free energy change for the formation of 1 mole of a substance in its standard state from its elements. So just as we have delta H of formation tables, heat of formation tables, we have free energy of formation tables. We can do the sum of the products minus the sum of the reactants for delta G. And again, just like delta H, since everything's a delta, elements in their natural state, the delta G of formation is 0. So delta G of elements in their natural state equals 0 kilojoules per mole. So that would be a different way to calculate delta G. And how you determine how to calculate delta G, just like calculating delta H, depends on what information you're given. So here I have a table of delta G values, so I can use those values to calculate the delta G for the reaction. So delta G equals the delta G of the products, which would be 2 times negative 27.2 minus 2 times negative 56.7, and the delta G of formation of O2 is 0. And you'll notice this unit is kilocalories. You will not see kilocalories except in this example that's in your thermodynamics notes. But that's okay, it works the same way as kilojoules. As long as all the units are the same, the math works the same. And in this case, the delta G equals negative 59.0 kilojoules per mole reaction. This is negative, so this reaction is thermodynamically favored. Okay, so two ways so far to calculate delta G. Use delta G equals delta H minus T delta S, or use delta G equals delta G of the formation of the products minus the delta G of the formation of the reactants. There is a third way to calculate delta G, and you will recognize this. It's simply an application of Hess's law. Just as we can use Hess's law to calculate the delta H for a reaction, we can use delta G to calculate the heat of reaction for a reaction, or the heat of the free energy of formation based on a reaction. So the reaction is actually missing up here. So what I want to do is change graphite into diamond. So that's the process I'm looking at. So carbon, graphite, this is not gas, but graphite, changing into carbon, diamond. So, if I look at this, the first reaction needs to be flipped. CO2 yields C diamond plus O2. Since I flipped the reaction, the delta G becomes positive 397 kilojoules. Graphite is a reactant, so C for graphite plus O2 yields CO2 gas. This delta G stays the same. And then if I add these up, the CO2s cancel out, the O2s cancel out, so carbon from graphite, carbon to diamond, has a delta G of positive 3 kilojoules per mole reaction. So that is not thermodynamically favored.